Good morning, friends. It gives me immense pleasure to be here again for my course, which is Engineering Thermodynamics. As of now, I have completed the nearly 55 lectures. Today is another area of this course that is called the definitions and terminology. In this, we will be discussing about 5 lectures, Module 1, Module 2, Module 3, Module 4 and Module 5. In this, we will be only talking about some important terminology used in the thermodynamics and there are some definitions. Today, I am in Module 1. This module is related to the basic concept of thermodynamics. In this, we will be discussing some very important definitions of Module 1 and their terminology. So in this, we will be seeing some definitions of some basics of thermodynamics, definition of critical points and triple points, and there are so many other things that I have not mentioned here, but we will be talking about different definitions of engineering thermodynamics. So definition and terminology, we will be see the pure substances. So pure substance, we can see here with the diagram that here we have the air. Air consists of nitrogen and air. We have two separate gases. So a pure substance that has a fixed chemical composition throughout is called the pure substance. Water, nitrogen, helium and the carbon dioxide, for examples, are the pure substances. In this, the chemical composition is fixed. It will not vary. Like nitrogen, it is N2, water H2O. So this hydrogen and oxygen will remain the same in its all configuration. So here we can see the water vapor. Let it be vapor or the liquid. Here it will be the combination of hydrogen and the oxygen. If it is air, air also can be as a form of vapor or as a form of the liquid, but its configuration will be same. If you see here, we have the nitrogen here and the air. So air will have some percentage of nitrogen and some percentage of oxygen, and it will remain in the same form. So like this, we say that it is a pure substance. A mixture of liquid and the gaseous water in a pure substance, but a mixture of liquid and the gaseous air is not. So a mixture of liquid and the gaseous water is a pure substance. So this is the pure substance, but a mixture of liquid and the gaseous air, in this, the second one is not the pure substance, because air has got some nitrogen but water has got the hydrogen and oxygen, but air has got nitrogen and air. So this both are not. One is the pure substance and another is not. So now define the phases of the pure substances. So we will see here that we have the 3 phases. All the 3 phases we are going to discuss in today's. So here substances exist in the different phases. At room temperature and the pressure, copper is a solid, mercury is a liquid and the nitrogen is gas. So here we have the solid, liquid and the gas for the same temperature and atmospheric pressure. Under different conditions, each may appear in a different phase, even though there are 3 principal phases, that is solid, liquid and the gas. A substance may have several phases within a principal phase, each with a different molecular structure. So here we can see this is the solid, this is the liquid and this is the gas. So at room temperature, copper is solid and mercury is the liquid and then nitrogen is gas. Under different condition, each may appear in a different phases. So if you heat it, your solid may also become liquid. but you have to heat like your copper. If you are heating the copper, initially it is a solid, but if you heat it at 1000 degree or 1100 degree, it will become the liquid. And further, if you make it 3000 and all, it will become the gas. So anything as per the temperature and pressure, their configuration may change. So here you can see the solid has got some specific lattice form. Liquids are in the different, they have more spaces between molecules, and gases are having much more than the liquid, and they are roaming very fast and they are hitting the wall very randomly. Now define the compressed liquid and the saturated liquid. So what is the compressed liquid? Liquid at a low pressure and the low temperature, say at atmospheric 1 and 20 degrees centigrade. Under these conditions, water exists in the liquid phase and it is called the compressed liquid. So if the temperature and the pressure is at atmospheric, you put the water. For water is in the pure liquid state, and this is called the compressed liquid or a subcooled liquid, meaning that it is not about to vaporize. So if it is low temperature, your water will not vaporize, and if it is very low, it may become solid. But if it is somewhat higher, 40 degree or 50 degree, 60 degree, it will start vaporizing. So at 40 degree, it will start vaporizing. So saturated liquid. So what is the saturated liquid? It is a liquid that is about to vaporized. At 1 atmosphere and 20 degrees centigrade, water exists in the liquid phase, that is called the compressed liquid. At 1 atmosphere pressure and 100 degrees centigrade, water exists as a liquid that is ready to vaporize. That is called the saturated liquid. And this saturated vapor, a vapor that is about to condense. So saturated liquid, a liquid that is about to vaporize at 1 atmosphere and 20 degrees centigrade. Water exists in the atmospheric condition. If you put the water, there will not be any vaporization, but at the same pressure, atmospheric pressure, and you increase the temperature to 40, 50, 60, 70, 80, and when you reach to the 100 degrees centigrade, this water will start vaporizing and your whole water will convert to the saturated liquid. So it is ready to vaporize. That is called the saturated liquid. And the saturated vapor, a vapor that is about to condense. About to condense, it is called the saturated vapor. So here we can see that this is here the saturated water and this is the saturated liquid. So in the left side of this dome, below the critical point, it is a saturated liquid line, and right side of this dome, it is a saturated vapor line. So in this way, we can define the compressed liquid and the saturated liquid. There is a difference between the compressed liquid and the saturated liquid. This saturated liquid means it start vaporizing. If you see here, it is a compressed, but as it is touching here, it is saturated liquid. So here we have shown the PV diagram of a vapor cycle in this system. So here, as you move towards this, it is saturated vapor. As you move towards this, it is a saturated liquid. And in between here, we have the mixture of liquid and vapor. Now we have to see another very important definition, that is the critical point and the triple point of the system. So here we can see that the critical point, the set of condition under which a liquid and its vapor becomes identical. See phase diagram. For each substance, the conditions defining the critical points are the critical temperature, the critical pressure, and the critical density. So this you can see here that the critical point here, this is here. Okay, this you can see. This is the critical point. This point here, if you go towards this left, you will get the liquid. If you go towards the right, you will get the fluid. So liquid and the fluid will be joining. That is called the critical point. So the set of conditions. So in this, it may be the pressure, it may be the temperature, and it may be the density. The set of condition under which a liquid and the vapor becomes identical. So in this case, in this point, liquid and vapor are identical. You cannot identify which is the liquid or which is the vapor. And the critical pressure and the critical density. And if you, triple point, it is in this, the critical point, we have the two phases, that is a liquid and the vapor. But in the triple point, you have the three phases, solid, liquid, and the gases are combining together, and then we say that it is a triple point. So the triple point of a substance is the temperature and the pressure at which the three phases, that is gas, liquid, and the solid of the substances coexist in the thermodynamic equilibrium. It means at which temperature or the pressure the solid, liquid, and the gases are in the same state. That is called the triple point. The triple point of water is used to define the Kelvin. That is the Kelvin, that is the absolute temperature is defined. The base unit of the thermodynamic temperature in the international system of unit. And by the help of this triple point of the water, we have assumed that this is the absolute temperature, and it is unit of this thing is the Kelvin, and which is nowadays used for international system of units. So here we can see that in this triple point, this is the vapor, this is the liquid, and this is the solid. So here all the three phases are existing in this zone. So this point is called the triple point, which is mentioned here, which is a very important, because the triple point of the water gives the relation of Kelvin, that is the absolute temperature in a thermodynamic system. Define temperature and the temperature scale. So we know that the Zeroth law of thermodynamics, by the help of the Zeroth law of thermodynamics, we have defined the temperature, and this temperature we can give with the help of the comparative study. So we will see that what is the temperature. Temperature refers to the measure of the hotness and or the coldness of an object. In other words, it indicates the amount of thermal energy an object contains. The SI units to the measure of temperature is Kelvin. Degree Celsius is another commonly used in metric system. So if you see here that one object is A, another is the B. If you touch this A, you will feel some hot, and if you touch the B, you will feel some lower hotness. So by this sense, you can see that it is more temperature, and this is the less temperature. So it is a feeling of hotness or the coolness of an object. It indicates the amount of thermal energy. So if it is high temperature, the thermal energy of this thing A is greater than thermal energy of the B. So this indicates, and the units of SI unit is Kelvin and metric unit is degree centigrade. These are the units. So what are the scale of the temperature? A temperature scale. A temperature scale is the calibrated system for measuring temperature, making it necessary for studying changes in temperature and heat transfer. A temperature scale is a calibrated system for measuring temperature, making it necessary for studying changes in temperature and heat transfer. A thermometer is an instrument that uses a temperature scale to measure temperature accurately. So for this scale we use the thermometer, and this temperature scale is a calibrated system of measuring the temperature. How we can see that it is a 0 degree or it is 100 degree? So as and when if you give the heat and it is start boiling, that point is the 100 degrees centigrade, and at which it is in the liquid form or in the saturated form, that we say that it is a 0 degree. So like this we calibrate different thermometers. Any physical property that changes with temperature is called the thermodynamic property. So if any physical property which changes with the temperature is called the thermodynamic property. So this temperature is very important parameters for thermodynamics. That is why it is, because it will change its energy level, and that is why it is very important thermodynamic property of the any system. Now we have to define another very important, that is called the thermodynamic thermocouple and the working conditions. So here thermocouple thermometer, it is used for a high temperature devices to measure the temperatures of engines, gas turbine engines, and in hot zones. So a thermocouple is formed by two types of wire which are made of different metals such as copper and the iron. So if you take one wire of iron, another wire of here, it is a copper, and you join together here and put inside the furnace or engine. So there will be a transfer of heat, and as per that, the two ends of both the wires meet to the one junction, that is the junction 1. By this, the condition for the thermocouple, that is thermometer to work, both junctions will each produce a small EMF with a difference in temperatures between them. So if you put a here plus or the minus, voltmeter will indicate some EMF, electromotive force, or the voltage is generated. So the temperature can then be calculated using a millivoltmeter. So here we can write a MV, the millivoltmeter, which will read this value. One junction usually remains at a fixed temperature, while the other is used to measure the unknown temperature. So here is the unknown temperature, and this is here, this end is a known temperature. Known temperature, that is atmospheric. The equation is E alpha delta V. So E is equal to EMF generated. Delta V is a difference in the temperature between both the junction. So this is the alpha is the conductivity here. So in this way we can measure the temperature by using this voltmeter. Voltmeter can be calibrated as so that it can define the temperature, and which is converted into electrical signals. Define a specific gravity and a specific weight. So we have seen some definition as of now about the temperatures. Now we will go for some other definitions, that is called specific gravity and the specific weight. So sometimes the density of a substance is given relative to the density of a well-known substance. So we take the density. So per unit volume, what is the weight of this any system is called the density. But this density we can measure with respect to the another known density, that is called specific density. So sometimes the density of a substance is given relative to the density of a well-known substance, then it is called the specific gravity or the relative density, and is defined as the ratio of the density of a substance to the density of some standard substance at a specified temperature. So it is the ratio of the density of the substance to the density of the some standard substance at a specified temperature. So normally we take the water as a standard. So we take if specific this density of one is something divided by water, it will give. So if it is water by water, it is 1. So if it is less than water, it means the density of the substance is less than the water. And if it is more than the water, then the density of the substance or the relative density is more than the water. Usually water at 4 degrees centigrade, for which raw water is density of the water is 1000 kg per meter cube, that we normally take it. So specific gravity, we can write it that specific gravity is the density, this is the density of substance to the divided by density of the water. So in this way we can find out, and here I have given some specific density for some of the material. Water is 1, blood is 1.06. It means heavier, blood is heavier than the water. Sea water is 1.025. Gasoline is 0.68. Ethyl alcohol is 0.79. So these all are lighter than this gasoline and ethyl alcohol. They are lighter than. Mercury is very heavy, 13.6. Balsa is very, very light, 0.17. That is why for our aero modeling and all we use the balsa wood. Dense oak wood is 0.93. Gold is heavier than the mercury. It is 19.3. Bones are 1.7 to 2.0. Ice is 0.916. And air is 0.001204. So these things are only for your knowledge, that water we take as a 1. If anything is this number, that is a specific gravity is more than the 1, it is heavier than the water. If it is less than this, it is less weight of that substance. And if you put the kerosene on top of the water, it will be floating on the water. It means it indicates that specific gravity of the kerosene is less than the specific gravity of the water. So these numbers are very, very essential to understand. So specific weight, the weight of a unit volume of a substance is called the specific weight or the weight density. And so per unit volume, the weight of anything per unit volume of a substance is called the specific weight or the specific density, and is expressed as gamma S is equal to rho g. It is Newton per meter cube. The densities of the liquid are essentially constant, and thus liquids can often be approximated as being the incompressible substances. So all the liquid, water or anything, their densities are mostly constant. So we can tell them that they are the incompressible. But if you take the gases, they are not incompressible from certain conditions. But most of the gases, the liquids are the incompressible, and solid, you know that it is already, you all know that it is incompressible. But gases are compressible of a certain velocity and certain temperature and other pressure conditions. Now I will define the Zeroth law and the conversion scales. So what is the Zeroth law? And this Zeroth law has made that the system's temperatures can be calculated with comparing to the some known parameters. The Zeroth law of thermodynamics states that if two bodies are in a thermal equilibrium with a third body, they are also in thermal equilibrium with each other. So the Zeroth law of thermodynamics states that if two bodies are in thermal equilibrium with a third body, they are also in thermal equilibrium with each other. So if suppose this is the body A, which is in equilibrium with body B. Now body B is equilibrium with body C. So we can say that the C is also equilibrium with A. So this is called the Zeroth law of thermodynamics. So if two bodies are in the thermal equilibrium with each other, with a third body C, then they all are in the thermal equilibrium with each other. That is the Zeroth law of thermodynamics, and these thermometers are made as per that only. So if you see the thermometer, we are putting something here, that is mercury, and if you heat this will give the length, and this length will be directly proportional to the temperature, and we say that it is 100 degrees centigrade or 35 degrees centigrade for human body and all we observe in Fahrenheit. So this is the definition of the zeroth law of thermodynamics. By replacing the third body with a thermometer, the zeroth law can be restated as two bodies are in the thermal equilibrium if both have the same temperature reading, even if they are not in the contact. So this is also another way of explaining that if the two bodies having differently the same temperature with the third body, we can say that all are in the equilibrium. So now conversion of temperature scale, we have one example. So during a heating process, the temperature of a system rises by 10 degrees centigrade. Express this rise in temperature in Kelvin, Fahrenheit, and so this temperature rise of system is to be expressed in different scales. This problem deal with the temperature changes which are identical in Kelvin and the Celsius scale. Then delta T in Kelvin is equal to delta T in degree centigrade. So both will be at 10 degree centigrade is equal to 10 degree Kelvin. The temperature changes in the Fahrenheit and the Rankine scales are also identical and are related to the changes in Celsius and the Kelvin scales. So delta TR is equal to 1.8 delta TK. So here it is a 10. So 1.8 into 10. So it will be 18 Rankine and this will be 18 Fahrenheit. Okay, so like this we can demonstrate. So now I will go for the next problem. First law of thermodynamics we have to define. It's nothing but the energy balance for the control mass system. So it is a conservation of energy law, means energy cannot be created and cannot be destroyed. Let us say that there is a control mass system. Some energy enters and some energy leaves this system. We can say that rate of energy in minus rate of energy out is equal to change of rate of energy of a system. Mathematically, this we can write it as a E dot in minus E dot out is equal to E dE by dt of the system. So here we can see that energy in, energy out. So making the assumption that within the system the energy is same everywhere, it is like a lumped to consider or deal with a group body. There will be unique of E. This is the function of the time, not the space. That is dE by dt system meaning. We can draw the analogy of a bank account like here. This we can see that rate of money in minus rate of money out is equal to total money balance in the account. So here dE by dt, this is the balance of amount per unit time. Bank also gives interest. This is like energy generated is net money in is more than the you have deposited. So a very good example of the conservation of energy by the bank balance. How much amount you are putting in, after 6 months if you are taking same amount out, you will get still some money will be with you. That is the energy generation which is part of your system. By entropy and some issues are involved. So now define the internal energy U or specific internal energy small u. So it is an intermolecular form of energy. The energy in a system arising from the relative positions and interaction of its parts. The internal energy of a thermodynamic system is the energy contained within it. In an isolated system, the internal energy is constant. It is the energy necessary to create or prepare the system in its given internal state. So it is the internal energy which is present inside the system, and it is necessary to create or prepare the system in its given internal state. So here we can see that the many thermodynamic processes, the change in kinetic energy, potential energy are the negligible as compared to the other effect. So we can write that this dE is equal to du, where U is a internal energy, specific internal energy, when potential energy and the potential energy and the kinetic energy Ke limit tend to 0. So del Q is equal to du plus del W. Here we are writing du, but here we are writing del because U is a property. So this is the first law of thermodynamics for all processes. So assumptions here we have made the kinetic energy and potential energy are not negligible, but their changes in the kinetic and potential energy are negligible. That is the important. So means delta PE and delta KE are negligible changes. That assumption if you make, you will get this equation. So del Q is equal to du plus del W. Du plus del W, where W is a work, W is a work, Q is equal to heat, and U is equal to specific internal energy. So definition of specific heat, that is the Cp and Cv we are using, specific heat at a constant pressure. So the specific heat of a gas at a constant pressure is defined as the quantity of heat required to raise the temperature of unit mass of the gas by 1 degree. The pressure remaining constant during heating, it is given by the symbol Cp. So if you take a 1 meter square of any material, and if you raise a 1 degrees centigrade, 1 kg of weight of this material, and how much temperature it is raising, how much heat is required to raise the temperature of 1 degree centigrade for 1 kg of material. That is called the Cp. It gives the heat holding capacity of the system for a gas. Observation on the Cv and the Cp, and at a constant pressure is a Cp, and when it is a constant volume, it is a Cv. So in the Cv we don't have to do any work because the volume is constant, we cannot produce any work. So if the Cp is greater than the Cv, so why the Cp is the greater than the Cv? During constant pressure process, volume changes is taking place and the heat is required more than the constant volume process, as in this no volume change and no work is done. But in the constant pressure process, work is also done. Greater heat supplied needed in a constant pressure process. So if I draw here PV diagram, so if it is, this is the constant pressure Cv and this is here, you will get the Cp. So here the volume changes V1 to V2, but here V1 is equal to V2. So no volume change. So in the CV, no work done. But in CP, there is a P into V2 minus V1 work is done. So you need to supply more heat on the CP. So CP is higher than the CV. So this is the reason that why the CP is greater than the CV. So here we have the two types of the gases are there. One is monoatomic like helium, argon, etc. Only translational motion of the molecules are present. CP and the CV are virtually independent of the temperature and remains constant. So if it is the monoatomic, that time CP and the CV will remain constant, and other than this diatomic or other things, CP and CV will not remain constant for all the conditions. So in the next class we are going to discuss about the definition and the terminology of the module 2. In that we will be discussing about the second law of thermodynamics and their related definition and the terminology. References I have taken the P.K. Nog, Engineering Thermodynamics, Tata McGraw-Hill's, then Eunice Senegal, Michael Ebor's Thermodynamics and Engineering Approach, Tata McGraw-Hill's 7th edition. Any questions you are welcome to ask. It will be my pleasure to reply. My email ID is dwivedi@gmail.com. Thank you very much for the joining. Please do like and subscribe my channel. It will be giving you a lot of pleasure for me. Thank you very much.
Like, share and subscribe. Hit the bell icon for more updates.